Welcome to another video. Today we will go through the art of slashing analysis. Ethereum is a technology that lets you send cryptocurrency to anyone for a small fee. It also powers applications that everyone can use and no one can take down. It's the world's programmable blockchain and a marketplace of financial services, games, and apps that can't steal your data or censor you. Ethereum also has its own cryptocurrency, Ether. Check out more about Ethereum on ethereum.org. Today we will look at the data set that is obtained from Beaconscan Block Explorer. It has information on 1751 slash validators. Being slashed means that a significant part of validator stakes is removed, up to the whole stake of 32 ETH in the worst case. Validator software and staking providers will have built-in protection against getting slashed accidentally. Slashing should only affect validators who misbehave deliberately. For more information, please visit this website about slashing. So why do validators get slashed? There are a few reasons. By being a proposal and sign two different beacon blocks for the same slot, by being a tester and sign an attestation that surrounds another one, or by being an attester and sign two different attestations having the same target. Let's get started. Let's load the data and look at the first few rows. So we have a few columns here. We have the row index, we have the epoch number that the validator was slashed, the slot number that the validator was slashed, the amount of time passed since the validator was slashed, the index of the validator who was slashed, the index of the validator who did the slashing, and the reason why the validator was slashed. So let's look at some high-level statistics. We're going to use the library scheme R, and we can just say scheme of the data set, which is df slash, and it will give you several statistics. So we have two character columns, and we have 5 numeric columns, and these are its statistics. Let's get the number of unique values in each column. We simply can use summarize all and end distinct function. So we have the data, and we can do summarize all, and the function is end distinct. And this will give you the unique values, number of unique values of each column. So we have 7051 unique X indexes, we have unique 1647 validator who was slashed, and 1771 unique slasher. And there are only 2 reasons. Now let's find out how many validators are slashed over time. At first, we can sort the data by using the arrange. So we can do slash arrange by the epoch. Then we're gonna group by epoch, and we're going to just count them using summarize. And let's look at the first few rows of this. So in the epoch 4, there's one person being one validator being slashed, and so on. We can also plot this using ggplot. So let's see. So we can do num slash. We can do ggplot. We can do x equals to epoch, y equals to the count. And then we just do a jump line, and we can get the time series. Okay. Of course, we can add more ticks to the x and y axis using scale x continuous and scale y continuous. We can do scale pre-breaks n equals to 10, for instance. We can do the same for y. And just copy that. And we can also add a nice title to it. Right, so it's a number of slash over epoch, for instance. Okay. So you can see we have more ticks now, we have a nice title, and so on. Right, to better assess the impact of these spikes here, we produce a cumulative plot. So let's see. We can do num slash. First, we need to create the cumulative count column using the cum-sum count. Then we can use ggplot. Again, x equals to epoch, but now y is equals to the cumulative count. And again, we're just going to draw a line. Okay, looks something like this. I see you can see the first large spike is around 3,000, and another one is around 12,000 or so. Okay. Again, we can include more takes, just like before. So something like this, right? A number of slash over epoch. Okay, so we have a pretty good graph here. Now let's investigate how often a slash occurs. Let's see. So first we need to create previous epoch, which is just shift the epoch one row up. Let's do that. So let's call that epoch elapse. We have the data. We're going to create previous epoch using the tail, and then we're going to subtract 1, and then we fill in the last with 0. And then the next step is going to create epoch elapse by subtracting the previous epoch from epoch. So we take epoch elapse, epoch minus previous epoch. And then finally we looked at, we filtered it out to see the non-zero epoch elapse. Something like this. We can then let's compute the statistics. So epoch elapse. Go ahead and compute statistics by using summarize. Mean is equal to mean epoch elapse. We can do mean is equal to mean epoch elapse. Then max is equal to max of epoch elapse. So we see that approximately 40 epochs elapse between slashings on average. And let's plot the histogram to see. So to plot the histogram, we simply just use ggplot again. We can do the epoch elapse. Then we just use geom histogram. So we get this histogram here. Of course, we can make it a little pretty. I'll leave that up to you. Now it's your turn. Let's find out more about epoch elapse between slashings. First, verify the fact that 41% of the epoch elapse is 1. Then, draw a red time series of epoch elapse using previous epoch and give it a title. Okay, pause the video and come back when you are ready. Get the percentage of each epoch elapse. We can simply do summarize again. So we can do epoch elapse. We first group by epoch elapse again. And we use summarize. First, let's count them using n parentheses. And then we can create a new column called percentage by simply divided by the total times 100. So we have the epoch elapse, we have the number of those epoch elapse, and then here's the percentage. So it's approximately 41% for the first epoch elapse. Okay, so to draw a time series is very similar to what we had just now. When we drew time series, we just use ggplot geom line. Right, so ggplot aex, x is equals to previous epoch, y is equals to epoch elapse, and we just do geom line. But here we want a red time series, so we have to do color red, and let's give it a informative title. Time series of epoch elapse between slashing. There we have it. We have a red time series. Also, again, you can use a similar technique to get more ticks on the x and y axis. So why are these validator slash? Well, there are two reasons they are in this data set. Let's create a histogram to show the distribution of these two reasons. So we can just simply do the data set, we group by the reason. We count and count both of them, right, using again the n parentheses. Now we have the numbers and the reasons, so we can just plot them. So we have the x reason and y equals to the count. We can do the column, and let's see what it looks like. So it looks like that. We can make the width a little bit less, and also we can change the color to something like a steel blue, for instance. It looks like it just look a little bit nicer that way. Of course, we can give it a title and all that. Alright, so I'll let you try to do that. But let's also now try to get a percentage on these bars. So to do that, we need to use geom bar and use this count here. So this is the code. Right, so we're going to use geom bar. We're going to use count and then I'm going to use geom text. Right. So we're going to use we're going to create the percentage, and to get the percentage, we just this divided by the sum, and we use scales percent to make it a percentage, and then this is just to move it a little bit down to have it in an appropriate place. So once we have that, we're going to get 97% and 3%. So the distribution is skewed heavily to the attestation rule offense. But interestingly, this distribution has not been constant over time. But let's see how it changes over time. We can look at the number of slash over the reason. So we can do df slash, we create, first we change it to a factor using factor, then we group by, we use drop false to keep all the combination present, even if its count is 0. And then we use tally, which is just counting. It's just another way to do summarize and parentheses. And here's the first few rows. So you can see, even if it's 0, it will still appear because I put dot drop equals to false. Okay. So we have the epoch now, and then we have the number of reasons that correspond to it. Okay, so now we can produce a time series. So num slash over epoch reasons, use ggplot, x is equals to epoch, y is equals to n, we use group as reason, and we can give it different color depending on the reason, and simply just geom line. So it looks like that. We can barely see the proposal rule, so let's do a faster wrap to split them. Like that. So now it's split. But we can also make the Y scale different so we can see the changes on the proposal rule offense easier. So we can do scales is equals to 3Y. Now we can see the changes on proposal rule offense. Right? Despite the proposal rule offense being rare throughout epoch, right? But the first offense committed by validator on network is actually proposal rule offense. It's your turn again. Now create a time series of the cumulative number of reasons similar to the previous slide. Hint here is you have to use group by twice. I pause the video and come back when you are ready. So this is very similar. We need to create another column, right, which is the cumulative sum column. But before that, we need to group by again. Okay, these are the same code from before. We just need to create another column. Then we use the same we can use a similar code to plot the cumulative sum. So there you have it. Now we have the cumulative time series. Now let's turn our attention to the distribution of number of slashings received and the number of slashings performed. So here are the distribution. We can see that of the validators that have slashed, most have only done slashings once or twice. Similarly, most validators who have been slashed have received only 1 or 2 slashing, and only a handful of them have been slashed more than twice. So now it's your turn to recreate those plots on your own. The first plot you use geom histogram. The second plot you use the geom bar. Pause the video and come back when you are ready. Hope you got the plots. So first we need to group by slash by. Then we simply count how many of them. Then we just use geom histogram. And all these are just making it more ticks and giving it titles, all that. And all we got to do for the second plot is change slash by with validator slash. It's very straightforward. To learn more about the validators, we will bring in a second dataset that is obtained from the Beacon Scan Explorer. To learn more about the dataset, you can read our case study on it as well. So the dataset provides these columns. We have the row index, the public key, the index number, current balance, effective balance, the number of proposed blocks assigned, executed, and skipped. We have the eligibility epoch, we have the activation epoch, exit epoch, withdrawal epoch, and finally the slash indicator. We have the epoch when a validator was slashed and also their activation epoch. Therefore, the difference will answer how long before a validator gets slashed. However, we have validator who was slashed more than once. We will need to get the rows where the first slashing occurs for each unique validator. So these two are in different datasets, so we need to first join these two datasets. So these are the code. Right, we can just copy this. Right, we load the data. We're going to join it using the validator slash and the index, and we also converting genesis to 0, and that's it. So let's put it here and run it. So now we have the data set that we can use. Now we're gonna find out how long before a validator gets slashed. We will first create a time to slash by subtracting them. So we can do df join slash time to slash epoch minus slash activation. We can group by validator slash And then we're gonna use the minimum of each of these. So which min time to slash. Then we ungroup so that we can do some summary. So we have the min time to slash. Then we have mean time to slash, and we can get the max of time to slash. So we can get the summary. So on average, validators are slashed after 3,900 epochs. So note that this average accounts for only validator who are slashed at least once. Similarly, we can compute time to slash to find out how long before a validator slashes other. Right? All you got to do is just change a little bit of what we have. Okay. I'll let you think about it for a few minutes. You can pause the video and come back when you are ready. All we got to do is change slash by now, right? And again, instead of validator slash, we use slash by, right? And that's it. Right? Now we get that a validator marks their first slash within 3,400 epochs. Right? The fastest first slash actually only 4 epochs after activation. Okay, interesting. So we've looked at the distribution of the number of slashings performed by validators. Right, there was a validator that has slashed others more than 90 times. Right, so let's see who are the frequent slashers here. Since we have the data set, we can just easily get it by simply grouping and then arrange them by their slashing frequency. Right, so we have the data set already. So we have the df join slasher. We just group by slash by. Then we compute, we count them again using the n parentheses. Then we simply just arrange it by the frequency. And negative means a descending order. But then you notice that a lot of them are repeated because they are slashed by the same person. So we have to do the following. We have to select a certain column. So we have the slash by current balance, effective balance, proposed activation epoch, and slashing frequency. Then we use the distinct function to drop all the repeated rows. So here, the first page is the top 10 slashers. These slashers have similar current balance and effective balance. Most of them were also active for a long period of time. According to the tier system we created in the case study we did on the Validator Dataset, be sure to check it out. 8 out of 10 of these slashers are in the tier 3. Now let's try to visualize the slashing. Due to the single source structure of the slash by and validator slash columns, it allows us to treat the various slashes as directed edges in a directed graph. A directed graph consists of a set of nodes and directed edges, where the directed edges represent some relationship between the nodes. The nodes in this instance are the individual validators, and the directed edge exists between two nodes if one node has slashed the other. We will use the iGraph package to draw a directed graph. First, we will get the data frame using /by and validator slash. Then we will use graph from data frame to get the network object so that we can plot. So here's the codes. Note that the order does matter. Right? We want the directed edge to point at the validator slash. So let's go to our RStudio again. Let's run this code here. And so we use the /by and validator slash. Right? Again, the order matters. So here we use one of the layout is just a sphere layout. Right? Since this whole network comprises of too many vertices, let's decompose it to different subgraphs. We can use the decompose.graph and look at each of the component. So it turns out that there are 660 connected subgraphs. To look at these subgraphs, we can simply do plot the network and then we just use the numbers, right? So we have 1 to 660. So let's draw the first one. So the first one looks something like this, right? So we have 2 persons slashing to 2151, and it also slashes many other people. Let's now try to find the largest subgraph that we have. Right, so we can do this. Right, we can create a vector that gives you all the number of vertices, and then we loop through all the length from 1 to 660, and we simply do a vCount function which will count the number of vertices. And then we look at which of them is the max and what is the size of the number of vertices. It turns out that the 86 subgraph has the largest subgraph, which contains 415 vertices. Right? Here is the plot. So you can see here on this graph, you can see 1, 2, 3, 4, 5, 6, 7, 8 validators have done many number of slashes, and all of them have this star pattern. Now it's your turn. Find the second largest connected subgraph and its number of vertices. Then plot the second largest connected subgraph. Pause the video and come back when you're ready. So all we've got to do is just sort them and look at the second number. And we get 115. Then we simply look at which of them has the 115 by using which. So which is the 70th. So the 70th is the second largest connected subgraph. And we can use a similar code that we did for the 86th graph and replace 86 by 70. So here we have 2 vertices that slashes many other people. There were 2 interesting observations about the slashing behavior that were particularly important to understand the nature of the network visualization. The first was that there was not one validator that have been slashed by the same validator twice. The second observation we discovered was that there were no instances of revenge slashing in which a validator slashed a second validator and the second validator eventually slashed the first in return. When you combine these 2 facts, you explain why all the networks we produce were only simple directed graph, as in it doesn't have a loop or multiple edges. As the network of interconnected violators continues to grow, We expect the number of interesting subgraphs to grow with it, and represent some interesting dynamics in terms of the interaction between validators as pertains to slashing. I hope you enjoyed the video. I will see you next time.